Okay, so in this 1D kinematics constant acceleration, in addition to constant acceleration, constant speed question, we're looking at the 100-meter dash, and the simple model we're applying here is to assume constant acceleration until they reach top speed, which happens pretty quickly, and then they maintain that speed through the finish line. So what we're told here is the sprinter reaches a top speed of 11.2 meters per second in 2.14 seconds. What will be their total time? So in this question you sort of have to divide the sprinter's motion up into two different sort of phases, an accelerated phase and then a constant speed phase. So what we're sort of looking for is the time interval total is a time interval. Let's use A for accelerated phase and delta t(c) for the constant speed phase. And we already know the delta t for the accelerated phase, so we already know that this is 2.14 seconds, but we don't know the delta t for the constant speed phase. So the delta t for the constant speed phase would just be the delta x for that particular phase divided by the speed of the constant speed. Now we do know that. So we do know that this is we don't know how far the person moves when they're moving with constant speed, but we do know they will move at 11.2 meters per second. So our goal started with time, to figure out, total time. We're given the accelerated time phase, we don't know the constant speed phase. To figure that out, we just need to figure out the distance the person travels in that constant speed phase divided by the speed. We do know that. So now our goal is to figure out how do we figure out the delta xc. And this is sort of a good example of the process in which your priorities change. So in terms of variables, so our first variable was delta tc, then it became delta xc, and now you'll see it'll change again. The delta xc is equal to 100 meters minus how far they traveled during the accelerated phase. So now our new goal is how far does the person travel in the accelerated phase, and then you can sort of just work backward. So the delta x for the accelerated phase is vi delta t plus 1/2 a delta t squared. But we're going to assume the sprinter has to start from rest, so it's just 1/2 a of the accelerated phase times delta t squared. So delta x in this particular case is 1/2 a, so that's going to be a is going to be delta v over delta t times the same delta t squared, so we can get rid of those delta t's. And since it's going from rest to 11.2, this will be 1/2 of 11.2 meters per second. That will be their change in their velocity. And that happens over 2.14 seconds. So this is sort of equivalent to saying that the average speed would be exactly half of the final speed, which is true for something that's moving at constant acceleration, or half of the difference technically. So if something's moving from rest, it's half of the final, but it's technically half of the change in the velocity, the delta v, but the initial velocity here is 0. And this works out to be something around 11.98, so almost about 12 meters if we're so that's sort of the hard part. We've now figured out the distance that the person traveled, how much of the 100 meters they traveled during the accelerated phase. So the delta xc for is going to be 100 meters minus that 12 meters. So that gives them the 88 meters. The time interval that they will take to travel that far during the constant speed phase is going to be 88 meters divided by that 11.2 meters per second, and that takes them 7.9 seconds, 7.86 if you want it to be exact. And then if you go back all the way to the start and add the total time, add the 2.14 to this particular time, the 7.86, the delta t total works out to be pretty much 10 seconds, rounded to exactly 10. So 9.999 seconds. So it's sort of a 10-second 100-meter dash, which is very fast.